Yeah, so my talk was perhaps a little bit cryptic. Any Budweiser fans in the audience?
No.
I was thinking so, because I was a bit worried, right? Because the real thing was like, how did the universe go from Budweiser to, well, maybe some nice beer like Henrik or dark matter, which is brewed in Victoria, Vancouver Island, where I spent some time. But yeah, I didn't think it would be wise to have that online, so I decided to just keep the title a little bit vague, but here it's more graphic. So how did the universe change? Let's see. Because when we look at the very, very early universe, it's really very, very boring, very flat. So I would like to say the early universe is like Budweiser. It's not quite like water, right? Because you can see small temperature differences, but it's pretty close to water. And so this map is done by ESA's mission, in a way, many regards, you can see scientific precursor of Euclid, the Planck satellite. And so they measured very, very tiny temperature changes, differences in the afterglow of the Big Bang. And so this gives us the baby picture of the universe. And then when we look around us, so what is remarkable about it is that this is a great feat because you can fit a very simple model to these very, very complex data, because this is data of high quality, and these little fluctuations, you can look at the statistics, so that it's not completely random, there are correlations, there's typical scales, and those are the seeds of everything we see in the universe. But clearly, the universe, well, let's say for your neighbor, but hopefully you'll find that the people around you are not very boring, so it's much more interesting now. And so the real question is, how did the universe change from that into the complex world we see around us? Right? We see the world around us, much more complexity, much more diversity. You need many more numbers than 6 to describe it. And so how did that happen? Well, we have some good idea, because we know that from these very small density fluctuations in the early universe, roughly 380,000 years after the Big Bang, gravity pulled things together, and eventually gravity pulls things together and you can get all kinds of galaxies, stars, etc., etc. Except there's a problem. We know that the Big Bang happened 30.6 billion years ago. If we compute forward these small fluctuations that we see in the early universe, we would not be here today. There's a mystery, and the solution to that is this dark matter that Guadalupe already alluded to. So there's many ways how we believe dark matter must exist, but this is one of them. Dark matter is essential to form the structure we see today. So without dark matter, we would not be here today. And so relating that very, very simple early universe to what we see today tells us something about the ingredients of the universe, and that's really what Euclid aims to do. And so that's basically what we're trying to do, and this question was already asked, so how can we sort of figure out which is the right model? And essentially we're trying to reverse engineer this problem. So we can, and Mathieu Schaller is here, he does this for a living, he basically simulates universes in a computer. So you put a universe in a box, and you keep changing all the possible input parameters. You change the mix of ingredients, and every time you change the amount of dark matter, dark energy, or any of these other parameters, you end up with a different universe. And so what you see in particular is, so basically what you see here is two different universes, one with dark energy, one without. They start very similar, but over time they become different and different. And so as time goes forward, you basically go more and more to the present day. And you see that the universe with dark energy is much more clumpy. And that's because dark energy tries to push things apart. So in the current universe, dark energy is actually stopping gravity from creating bigger and bigger structures. So because of dark energy, structure formation is halted. And that's what we're trying to use with Euclid. So we're making this map of the galaxies and the dark matter, and look at how this balance changed over time. Because that's really what we're trying to measure. So basically it's like having the big brewer, like Heineken, which is like the dark energy, tries to make everything bland again, but at the same time you have the craftsman trying to make something that has a lot of interesting structure. So dark matter tries to pull things together, and dark energy tries to push things apart. That's in that sense that the yin and yang of cosmology. And so that's what people often ask. So what's the difference between dark matter and dark energy? Dark matter is gravity, trying to pull things together. Dark energy, we think, is a property of space. We really don't know what it is, but we think it's a property of empty space, and it tries to create more and more space wherever it can. And so really this is like this cosmic tug of war, and over time that balance changes. And unfortunately for us, dark energy has won, and things get more and more and more boring again as the universe drifts away. But who knows, right? We don't really know. And so that's exactly the problem from the more observational side, because I'm trying to study the universe as an observational cosmologist, because most of the universe is invisible. And that's really difficult, right? So I'm looking at things you cannot see, trying to figure out how much structure there is. So how do you figure out structure when stuff is invisible? Well, there's still a little bit of froth. There are galaxies in the universe, and these galaxies, they're not located randomly. We see that these galaxies actually trace where the peaks in the dark matter distribution are. So basically our galaxy is surrounded by dark matter, but we can use our galaxy to pinpoint where there must be a clump of dark matter. The only problem is that the pattern sort of works, but it's not really a good indicator of how much dark matter there is. And this is a very good analogy, because we can fly over Earth, and we can look at Earth. And what we notice is that people live in cities. Because we fly over North America, you see these conglomerations. These are cities, so they're very clustered. People like to live together. And in between is very dark. And we see also a lot of light in these cities. Okay, so we've established that people like to live together in cities, and so where there's more light, there's more people. So we continue our flight and fly over India, and lo and behold, same pattern. Also in Asia, people like to live in cities. Well, that's great, that all works. And what have we else learned? Half the people in the world must live in North America, because that has half the light on Earth. And then we see the problem, right? The pattern may be stable, but the amount of light is not a direct indicator of how many people you have. There are other parameters. The same is true for galaxies. When we look at galaxies, you know where you see a galaxy there must be dark matter, but just by looking at the starlight, you don't know exactly how much dark matter there is. That depends on how the galaxy formed, how it interacted with its neighbors. So it's a very, very complex process. On average, you might be able to say something, but not for individual galaxies. But patterns, like cities, they might work. And that's one of the things we're trying to do with Euclid. We're trying to look at patterns. So going back to this cosmic microwave background, I said these temperature differences were not completely random. Certain regions where there's more matter correlate with other regions where it has more matter. And it turns out what we're seeing here are acoustic waves, these sort of sound waves in the very early universe, and the sound of that, so the spectrum of that, is telling us something about how much dark matter there is, how much dark energy there is. And so it gives us a lot of information. It gives us those 6 numbers very, very well. And as time goes on, patterns like that, so regions which are a little bit, and it turns out this is a very vast distance apart, but there are these waves going through the universe, and if you're in a spot, in a region that is denser, about, so I should do this in light years, about 500 million light years away, there's an excess chance of having other galaxies. That pattern is still there today. It's not as clear anymore, but it's still there, and that's what we're searching for with Euclid spectroscopy. So we see as the universe expands, you see this ring in the early universe, that ring gets bigger and bigger and bigger, but we can still effectively find those rings on the sky, those sound waves on the sky, the imprint of that in the galaxy distribution, and that pattern can be used to then see how the universe has been growing over time. But we can do a lot better, because I did not think weak gravitational lensing without reason, because I don't work on this, I work on something much better. Because I can see gravity. I'm using the fact, with Euclid, but also with earlier work, on the fact that gravity distorts space-time. You might not notice it, but if you look around you, you don't see the world as it is. You see it slightly distorted, because anything with mass changes the space around it. And light rays, as a result, have to change their paths slightly. But of course, we're not as massive as galaxies. When you're a big galaxy, you get these effects. You see, and we've had this whole quiz about gravitational lenses, so you all know about this. But you get this deflection of light rays. And these deflection, the amount of deflection tells us something about how much gravity there is. And we can use this effect. And a very good example of sort of trying to get a sense of what we're trying to do with Euclid, you can try at home when you take a shower, put some coins at the bottom of the bath, and so you can look at this coin, and if the water is completely still, you will see this nice round coin. But if you make some waves, and so in this case the lighting is not perfect, but imagine the lighting was such that you could not see the ripples, but you would still see the coin move and change shape. So you would know there's water. Right? You don't have to touch the bathtub to figure out there's water in the bathtub. You see the waves and you know there must, even though you don't see the water, you know there's water there because you know that the coin should have been round. And so that effect is exactly what we're using in weak gravitational lensing and what Euclid is designed to measure very well. We're not measuring coins, it costs coins, but every coin, every euro gets us a galaxy. That's about right. I think we'll do a little bit more than 1 billion galaxies. So that's a pretty good deal, a euro per galaxy. The water is dark matter, not sure that's a good deal, but basically you see the analogy. We're using these galaxies to sense dark matter because a change in shape tells us directly something about how the dark matter is distributed in the universe. And once we know that, we can see how the clumping of the dark matter is changing over time under the influence of gravity. And so that tells us about dark energy, tells us about dark matter, maybe about gravity itself. Now, a project like Euclid, you don't just start. It would be very unwise to just say, well, the idea is good, of course, but just to say, okay, let's do this, let's build it, let's go ahead. In the end, you need to build up experience, and the experience we build up over time is a series of surveys on the ground, and a very important one for me, but also for people in Leiden, although they're all in Bochum this weekend for a busy week, is the kilodegree survey. And one interesting thing we found is, when we looked at this, is how clumped the matter is, because that's the best thing we can measure. Especially with the surveys we have today. Euclid is vastly bigger, so is a factor of 100 more precise. But even so, we can, on small parts of the sky, a kilodegree, so 15 times less than Euclid, we can map the matter distribution and look how clumped it is. And that's what we measured, that's the clumpiness of matter. We don't use so well the amount of matter, but what is interesting, these are our measurements on how clumped the matter distribution is. And the big surprise was, even though it's still not super duper significant, is that when we compare to measurements from this Planck satellite, that we find that the universe appears to be less clumped. And we discovered this some time ago, and every time we fix the measurement, do better measurements, improve the analysis, we keep finding the same results. So this is very, very puzzling. So we're finding that the clumping seems to be a little bit less than what we naively expect. And if you read the abstract, I mentioned the interest in the IPA, and it's a bit of a stretch, but it turns out, right, this parameter, this clump, how clumped the universe is related to something about the initial perturbation amplitude. So basically, when we have this very early universe, we have these density fluctuations, these little differences between different places of the sky. They grow over time. We don't know what sets these amplitudes, but they're there. They're not interesting by themselves, but by comparing them over time, they get interesting, and that's really what we're interested in. So the IPA, the internet has so many beers with astronomy themes, it's really amazing. But basically, this is a sour India Pale Ale, and so maybe we have sour initial perturbation amplitudes, and so, because I'm not a fan of sour beers, but some do like it. The question, of course, is did we do something wrong in the measurement? Right? As I said, we've been trying to, we have been improving things, and it just doesn't go away. The interpretation of the signal is something that is also something that's not that easy, and it's also very relevant work for Euclid. I think it's okay for now, but who knows? Of course, I don't want to badmouth my colleagues that work on Planck, but maybe they did something wrong. Or, and that's perhaps the more exciting thing, are we seeing a first hint of something new? And although I won't talk about it further, but it actually turns out when we look at the expansion rate of the universe, there's also a bit of a crisis there. So there's some tension, as we call it, between different measurements. And what is interesting, it seems to be a difference when we look at the nearby universe. It's what we do with kids, what we do with the Hubble parameter, and this very distant universe. So maybe there's this evolution of the universe we might not quite understand as well as we think we did. So that's interesting. Well, the project manager is here, so I can't show you any Euclid pictures, which will kill me, but I can do the next best thing, because Euclid is really, very crudely speaking, like HST. And so I can't compare, I'm not going to compare to the slow digital sky survey, because it's not fair, because we're so much better than the slow digital sky survey. That would not do justice to what the amazing work they've done. But this is actually the best thing we can do from the ground. This is the Subaru Telescope on Hawaii, and it's an 8-meter telescope, very similar to the Vera Rubin Observatory, the telescope they have there that will come online next year. We have also some involvement there. We're building the all-sky monitor for that. But this is basically what the best ground-based data will look like. Okay, look very carefully. This is what Hubble looks like on the same part of the sky. Go back. Or do I really need to do a vote which one is better? Right? This is what Euclid data will look like on the same part of the sky compared to the best ground-based data on the same part of the sky. It's not exactly the same, but it's a pretty good analogy. So this is really, really, this shows really the improvement of Euclid for measuring shape, but so many other things. Right? So it's really an amazing, amazing data set. The real data look like this, but I can't show you because we would have to kill you all. But just to give you an idea what Euclid can do, like remember this tension. Right now we're really limited by the statistics of the data we have, because it's really interesting, but we need just much better data. This, I sort of gave an indication. And of course, the whole team with Guadalupe is working on the code that actually will do this properly, so I just drew a little square. But this gives an indication what the improvement of Euclid is, right? Our constraints go to this tiny little dot. So if it's new physics, we'll know it for sure, very, very quickly. And so this sort of gives an idea how much better Euclid is for this cosmology. And so, the real question is, what will we find? Because I think that is fair to say. We have no idea what dark matter is. Yes, well, dark matter we have some ideas, but dark energy we have no good idea. And Euclid is designed to really make a big step forward in the field. And so perhaps it's just a glass of Guinness, which is still the best model we have for the universe today. Or maybe it's something I don't like, it's sour, but it's strange, and maybe some people like pink stuff. So who knows what the universe is like? Euclid is the best bet for us to find out. And thank you very much for your attention.
Thank you very much, Henk. Can I just quickly ask, how long is it going to take us to find out? When will you be back here for Astronomy on Tap telling us the answer?
So the survey itself lasts about 6 years. The analysis might take some time. So yeah, it'll be, say, 8 years, might be the same bet.
Hang in there, folks. All right, questions?
I was wondering about how does Euclid measure distances? Because I know there's the cosmic ladder. Is it like the JWST is looking at the Lyman break, something like that, like in the redshift, in the spectrum?
Yeah, so we're measuring distances two ways. So one with the spectroscopy that was measured. So we're measuring the redshift. Not really. So when you have the when you're far out, then the redshift is sufficient. For the lensing, we're doing something a little bit cheaper because, so the redshift, you get 35 million redshifts, but a billion redshift is just way too hard to get. So we're using a trick called photometric redshift. So we're taking images also from the ground. So Euclid is not just, so we tend to talk only about the space telescope, but Euclid is much more than that. It's also a large collaboration with large ground-based telescopes to add information in multiple colors. And so these colors give us just enough redshift, just enough distance information to see how things are changing over time.
Thank you.
Usually cosmologists are ahead of observation, and then observation proved them wrong. So what is the idea at this moment that the cosmologists have about the clumpiness?
Yeah, so this clumpiness has sort of caught everybody by surprise, but the same is true for the Hubble constant, because it looked like when I studied, there was a factor 2 people, there was a camp of 50 and a camp of 100, then everything sort of ended up in the middle, and then since the last, it's 2015 or so, there's this tension again. So is it history repeating? We don't know. Yeah, people have plenty of ideas, but I don't think there's actually really one that really stands out. So in a way, we're in a very odd situation. Somebody's put it, we're living in the era of maximum ignorance, because we know that the current model of cosmology must be wrong. Right? So in particular particle physics. So the standard model of particle physics, right, even the Higgs they found, we can tell it's wrong. It can't be the right model. But we don't know what the alternative is. So in that sense, it's a very odd problem. We're in a very strange situation in science, and we know that's also good for job security, because we know there's something new to be discovered. But yeah, but what is sort of discomforting, we lack guidance. Normally you have a little bit of an indication where to go, and that's really what Euclid aims to do, is to provide that guidance into the future, which direction to search next.
The woman in the green? Yeah.
Have you, your topic implemented like AI technologies?
Yeah, so we're using that because Euclid is a very vast and complex data set, and so we are looking into ways to speed things up with artificial intelligence. On the other hand, I would say because it's complex, yeah, you have to have humans to really understand what is going on. Because it's, in a way, with machine learning, it's garbage in, garbage out. And the key of Euclid is to understand, really spending all the effort on understanding the data in all its details. That's why we're taking also, even now, we haven't started the survey yet, because we're taking a lot of additional data to really understand the telescope, understand the detectors. So it's a very complex process. This is why we take also these deep fields, etc. But we're using it mainly to speed things up.
And we also expect, like, when can we expect Hoekstra cosmology model?
I don't so much make models, but we'll constrain them. But the first results, so we have actually a number of data releases. So the first data release is sort of 2.5 years from now. So the 1 year data will take some time to analyze ourselves, to get familiar with it. I think that is actually arguably the most interesting first result, because that is such a step forward compared to anything else that has been done. And that will give us the first glimpse of the direction we'll be going. So in that sense, yeah, maybe, even though the final result will be in 8 years, I think the interesting result will be sort of 2.5 years from now.
Does Euclid give us more feeling about how homogeneous the cosmos is? We get the feeling that we see larger and larger structures, and that the scale of homogeneity is not completely understood up to now.
Yeah, so that's really the evolution. So indeed, Euclid goes to a much larger part of the sky and does that more precise, so we can push the limits of that. And then, but the real question is indeed is how that changes over time. So that's what Euclid will tell us, whether that is consistent with what we think it should be in general relativity, or if it's different.
Yeah, I think I had a similar question. If the first data release of Euclid is likely to show if dark energy varies over space-time or not, is that something that's expected? If it can show it's constant or varies?
Yeah, no expectations.
No expectations.
But in that sense, that's what I mean with sort of, in a way, the same was true for kids. We saw that tension from the beginning, and as time goes on, we've been shrinking things and so on. But yeah, it would be really bad if we find this kind of tension at the end of Euclid, because how do you continue? And so in that sense, the ideal scenario, but again, we'll get what we get, but the ideal scenario would be that we find an indication early on, because then with more data we would confirm it ourselves. There's other ways also we can interpret the data also better, so that's basically what we're trying to do also with my group here, is to push to smaller scale, so understand the astrophysics of things. So there's, like as I said, the interpretation is very complex. So we can push a little bit further, but in that sense, I think that the first release hopefully would give us a bit of an indication where to go. But we'll have to wait for that.